Hello everyone. We'll start with our next numerical on stiffness matrix method. That is, you have to analyze the sway frame using stiffness matrix method now. So one sway frame is given to you, that is ABCD, loaded with UDL on your span BC, and a lateral load of 100 kilonewton is applied at your joint B there. Okay, in between span AB and span CD there is no loading provided to you. So you have to analyze this frame by using stiffness matrix method. Okay, so we'll start with that. So first step in that is you have to calculate the degree of kinematic indeterminacy decay. So for calculation of decay, the first thing you know that if your frame is a sway frame, your decay value increases by 1 over there. That is, your sway coefficient delta comes into effect there. Okay, so if you calculate decay for this frame at your joint A and D, both are fixed, so your decay will be the 0 there. Okay, but at C and B joint, your joints are treated as rigid joints, so decay value will be 1 at each joint, plus along with that, due to this swaying coefficient, your decay will increase with 1, so total decay value that will come equal to 3 here, and those will be your value of first one, that is theta B. I'll assume that as clockwise rotation. Second, that is your delta B. Suppose I assume that towards the rightward side, and the third is the theta C. Again I assume that towards the clockwise direction over there. Suppose I assume this as D1, this as D2, and this as D3. So I'll mark the coordinates in this, that is coordinate number 1, coordinate number 2, and coordinate number 3 over there. Okay, so my first coordinate, that is the rotation at point B. Okay, so first is the rotation at point B here. Next, second is the horizontal deflection, or as compared to this, that will be a horizontal force acting at your point B again, that is your second coordinate. So here I'll note that as second coordinate in this way. Okay, same we have done in case of spring stiffness coefficient numerical. Next is your theta C, that is your third coordinate at point C, again a rotation, so third will be at point C. So these three coordinates will be my redundant reactions over there, or redundant unknowns over there. That is joint 1 theta B, again second that will be your delta B, and third that will be your theta C. Right, now we'll move to your second step, that is your for basic equation, that is your F is equal to ADL plus S into D. Okay, so we'll calculate first, that is F matrix. Now if you see, you are having three redundants over here, so here your F matrix will be in terms of F1, F2 and F3 here. Okay, is equal to, now what you have to see here, whether any corresponding forces are acting at your selected coordinates or selected redundant points or not. Okay, so your first, what your selected redundant, that is the theta over there, so what you have to see, whether a corresponding moment is acting at your first coordinate. Then second is your displacement, that is delta over here, so what you have to see, whether any corresponding force is acting over here. And the third is again the theta, so whether what you have to see, whether any corresponding moment is acting at your third coordinate or not. So we'll see that. So at your first coordinate, is there any moment acting here? No, it is not acting, so here your F1 value will become 0. Next, for D2 you have to check whether any corresponding force is acting or not. Yes, it is acting, a load of 100 kilonewton, so that you will be noting as your F2 value. Okay, now about the sign of this 100, now if you see what your direction you have assumed towards the right, and the actual acting direction of this 100, both are same, so this 100 will be treated as positive. If your direction is opposite to your assumed direction, then that will be negative 100. Okay, next is F3, that is you have to see corresponding moment acting at your joint C. No, there is no moment, so again your F3 will also become 0. So F matrix I am getting as F1, F2, F3 as 0, 100 and 0 again. Right, now so your first matrix is done here. Now we'll proceed to our second matrix, that is ADL matrix. Again we'll be having in that three values, ADL1, ADL2 and ADL3 over here. So we have to calculate these three values over here. Now ADL1, that is your selected rotation over here, so that will be your combination of moments acting at this point, that is MFBA and MFBC, friction moments of BA and friction moment of BC. Same way ADL3, that will be your combination of MFCB and MFCD. Okay, but if you see for ADL2 value, this ADL2 value, that is the selected redundant is the displacement over here. So what you have to see, is there any corresponding force acting in your restraint diagram or not. Okay, that means you need to calculate the horizontal reaction coming at this point B to get the value of ADL2. We'll see that. Okay, so we'll see first ADL1, or we'll calculate all the friction moments first. Friction moments here. So first friction moment, that will be your MFAB. Okay, UDL, no loading is provided in AB. Okay, so here your friction moment of MFAB and MFBA will be 0. Same way your friction moment of MFCD and MFDC will be also 0, because there is also no loading provided. Okay, remaining is MFBC. In MFBC, what is given to you? UDL is provided throughout the span. So for UDL, that friction moment you will get as minus WL square divided by 8. W is your 60, length is 4. So 60 into 4 square by 8, that I am getting as minus 80. Okay, and last is your MFCB, so that I'll get as plus WL square by 8, that is equal to plus 80 over there. So these will be my friction moments. Now ADL1 value. So ADL1, now I will not draw the restraint structure diagram over there. You have understood that how to calculate the ADL1. No need of drawing those diagrams again and again. So ADL1, that will be at your first coordinate. So that will be your friction moment of combination of MFBA plus MFBC. Okay, I'll calculate this. MFBA I am getting as 0. MFBC I am having as minus 80. So ADL1 I am getting that as minus 80. Okay, next I have to calculate the ADL2 value, but for ADL2, that is with the corresponding force you have to calculate there. So for that I need to calculate the corresponding force coming at this joint B, that I have told you that the horizontal reaction at point B will be your value of ADL2, that is you have to calculate the HB value here. So we will calculate that. Suppose this is your joint or member AB, and here you are having this horizontal thrust, that is HB here, and length of this is your 4 over there. Okay, so along with that, at joint A you will be having this HA over there. Okay, and along with that you will be having friction moment coming at A and friction moment coming at B over there. But eventually what has happened, MFAB and MFBA both we are getting 0 over there. So these moments are coming directly 0. If in any numerical loading is provided over this span AB, then what will happen? These values will come over there, and that values you need to consider while calculating this HB over here. Okay, suppose this is your 30, this is your minus 30, so you have to consider those values here. Getting here you are having 0, so we will not consider those values, or if you consider, that remains 0 itself, right? So if you calculate HB from this by taking moment at joint A, that moment will also come equal to 0. Why? Because there is no any other loading other than 0 in this. So your ADL2 value you are getting directly equal to 0. Okay, in any numerical, your this HB value whatever you will get, you will take moment at joint A, summation of moment at A is equal to 0, treating clockwise moments again positive. So there that will be your MAB plus MBA and the loading moment along this point A you have to take, and you have to calculate in that HB value over there. But here you are getting 0, so that I am writing as 0. Next you have to calculate ADL3 value. So ADL3, that will be at your third coordinate, which will be the combination of friction moment of CB and CD. So that will be MFCB plus MFCD. MFCD is again 0 because no loading is provided in CD. MFCB I have got that as plus 80. So ADL3 I am getting that as plus 80 here. Okay, so I'll write those three values over here: ADL1, L2 and L3. ADL1 I am getting as minus 80, ADL2 I am getting as 0, and ADL3 I have got as plus 80. Next, we'll proceed to your third matrix, that is the S matrix. So here ADL is done. Now we have to see S matrix over here. So S matrix for your three redundants, that will be in this way: S of 1 1, next S of 1 2, S of 1 3. Next here we will be having S of 2 1, 2 2, S of 2 3, S of 3 1, 3 2, and S of 3 3. Means here you have to calculate the 9 terms in your stiffness matrix if you are having 3 redundants. That is, here you are having 3 redundants over here. So here this matrix will be of order 3 by 3. Okay. Now we'll see that. So in first row one, what we'll do? We apply unit displacement at coordinate 1, keeping other coordinates fixed. Keeping other coordinates as your fixed one. Okay. So here you have to keep other coordinates fixed. That means you have to apply the first coordinate unit displacement, that is theta b is equal to 1 here. So here I'll write, that is, you have to apply theta b is equal to 1, that is, or d1 is equal to 1 there. Okay. So I'll draw the diagram for that. This is my joint A, which is already fixed. D is also already fixed. What you have to do is you have to release your coordinate 1 and fix the other coordinate. So other coordinate is your 3 here, and you have to fix the joint B just for the second coordinate, that is for the horizontal swing, and you have to keep it released, that is for your translation rotations over there, right? So here that will be your joint B, and here I am having joint C, right? Now I'll mark my stiffness coefficients over here. So stiffness coefficient here, that will be your for the first rotation, second that is the horizontal, and the third that is the again rotation over there. So 2 theta and 1 is for the delta. Now I'll mark the points. So this will be S of, you are applying unit, you are calculating it at your first coordinate. First coordinate is for rotation theta, when unit displacement is applied at your first coordinate, so that will become S of 1 1. Next S of, you are calculating it for your second coordinate, that is at point B, when unit displacement is applied at your first coordinate theta b. Okay. And here that will become, you are calculating stiffness for your third coordinate at point C, when unit displacement is applied at your first coordinate point B over there. So that will become S of 3 1. So here you will get S of 1 1, S of 2 1, and S of 3 1. Now we'll see about the deflection pattern of this. Deflection pattern, that is for S of 1 1, you have to apply theta b is equal to 1 for this BA and BC member. So for BA, that will be originating from the outward side, so that will go towards this outward side over there, which will show this D1 is equal to 1 there. Okay. Next S of 1 1, that will be again following a clockwise path for BC member over there. Okay. So it is originating from downward side, so this will be from the downward portion, that is again D1 is equal to 1. So that will follow downward path over here. Now we'll calculate the values of this stiffness coefficient. So first that will be for S of 1 1. So S of 1 1, that will show near end for your joint B for members BA and BC. So S of 1 1 will be 4 EI theta B upon L for BA plus 4 EI theta B upon L, and that will be for BC over here. But theta B is here equal to 1 there. Length of BA and BC, if you substitute, both are 4 over there. So 4 by 4 plus 4 by 4, this I get equal to 2EI. Right? Next, about S of 21 value. We'll calculate S of 31 first. S of 21 I'll explain you. S of 31 corresponding to your unit displacement, this is applied at your farther end over there. So S of 31 will be 2EI theta B upon L, but that will be only for member CB. For CD member, this will be completely restrained over there. So for CD, this value will not come. Just S of 31 will be for CB. So 2 by 4, this will get as 0.5 of EI. Right? Now, remaining is the S of 21 value. Now for S of 21, this you have to calculate the horizontal reaction coming at point B over there. Okay, I have given you the 3 notes in your spring stiffness coefficient numerical over there, that if you are applying theta is equal to 1 and if you are asked to calculate the force coefficient for the stiffness matrix, then that force coefficient, it is equal to minus 6EI theta upon L square, whereas that theta will be equal to always 1. Okay, so if you refer that note properly, you will get that is S of 21 will come minus 6EI theta upon L square, where that theta will be equal to 1 there. So if I calculate that S of 21, that will be for same for joint B for member BA and same for joint C for member CD also. Okay, but CD is here completely restrained. So S of 21 that will be equal to minus 6EI theta B upon L square, and that is for member BA, because you are calculating it only for BA. So if you substitute theta B is equal to 1 and L is equal to 4, so minus 6 upon 4 square, this I am getting as minus 0.375 of EI. Minus 0.375 of EI over there. You can note down here, that is notes. In that note I have given you, see yesterday's paper I am having these 3 notes I have given. If you are applying theta is equal to 1 and if you are asked to calculate the force value as for your stiffness coefficient, that comes equal to 6EI theta upon L square. So here you can write using note number 1. Okay. So here my first 3 stiffness coefficients are done here. Now we will move for your second Roman, that is Roman 2. So for Roman 2, what you have to do now? You have to apply unit displacement at coordinate 2, keeping other coordinates again fixed over there. That means you have to now release joint B for horizontal sway, that is the translational displacement, and you have to fix it for the translation rotation here. So I will draw the diagram again. Now here your stiffness coefficient will be in terms of delta. So whatever swaying coefficient you will see, this was displacement pattern that we are taking for theta, that those were for your slopes over there. Now here those displacement patterns will be in terms of delta. So here what you have to do is you have to apply here this swaying of this frame due to this lateral load for delta is equal to 1 there. Okay, and you have to fix the remaining joints here, right? So we'll mark your stiffness coefficients again. The first coefficient is at your first coordinate point B, right? Second is at your again point B, and third that is at your point C here. Okay, this is your point B and this is your point C over there. So this will be S of stiffness. You are calculating for your first coordinate when unit displacement is applied at your second coordinate. This will become stiffness you are calculating at second coordinate when unit displacement is applied at second coordinate, and this will become S of stiffness you are calculating at third coordinate when unit displacement is applied again at second coordinate, that will become S of 3, 2. Okay, so here you are applying delta is equal to 1 now. Now as compared to this delta, what will happen in this member AB and CD? Due to this delta, it will follow translational path over there. That is, if you consider this member AB and this as member CD, due to the swaying effect over there, what will happen? This will be having a translational displacement of 6 EI delta upon L square and again 6 EI delta upon L square for both these members. For AB also and for CD also. So that will show the values of S of 1 2 and S of 3 2 over here. Okay, so I have given you again the notes over there. That is, if you see these notes again, if you are having delta is equal to 1, we'll see third note first. If you are having delta is equal to 1 and if you are calculating the moment as your stiffness coefficient, that gives value equal to minus 6 EI delta upon L square over there. That gives minus 6 EI delta upon L square. This minus will be plus or minus here. Okay, that will vary according to your sign conventions, because what here we have assumed that these stiffness coefficients always in a clockwise direction, and whatever these translation rotations we are going to get, those will be anti-clockwise in nature, because your frame is swaying towards the right direction. If it sways towards the left direction, then these directions will be, or these values will come positive in nature. Okay, so if you see this third note, that is if delta is equal to 1 and if you are calculating moment for the stiffness coefficient, that value comes equal to plus or minus 6 EI delta upon L square over there. So that we'll use over here for calculating S of 1 2 and S of 3 2 values. Okay, so first value S of 1 2, that will come equal to 6 EI delta upon L square as per your note number note number 3 here. That comes equal to 6 EI delta upon L square. Now we'll see about its sign over there. Now if you see this S of 1 2, we are assuming that in clockwise direction, but this translation rotation, when your frame sways towards the right, it will be in the anti-clockwise direction over there, right? So this will come negative, that is opposite directions are here, so it will come negative. So this I am getting as minus 6 EI delta upon L square. Okay, whereas this delta will be here equal to 1. So if you substitute this, that will be for which member? That will be for member BA. Okay, so substitute this L square, this I am getting S of 1 2 as minus 0.375 EI. You have to check whether you are getting equal to S of 1 2 or not. That is in your first case. See here. Same I am getting S of 2.375 negative. Here also I am getting 0.375 negative. Same is the case with the value of S of 3 2. That also I will get here same value. So whatever this value of S of 1 2 I am getting, same will be your value of S of 3 2. That is minus 6 EI delta upon L square. Just that will be for member CD. Okay, so for CD, length of CD is your 2 meters. So 6 divided by 2 square, I am getting S of 3 2 as minus 1.5 EI. Minus 1.5 EI. Now the remaining value is about S of 2 2. Now S of 2 2, that is what, when you are applying delta here equal to 1 and you are calculating the force coefficient now. So you have to use the note number 2 here. Okay, when you are applying delta is equal to 1 and you are calculating the force as your stiffness coefficient, that value comes equal to plus 12 EI delta upon L cube over there. I have explained you yesterday how this value comes. You can refer that video lecture again of stiffness spring coefficient. So if you are applying delta is equal to 1 and you are applying force as your stiffness coefficient, that value comes equal to 12 EI delta upon L cube. So this S of 2 2 will be equal to 12 EI delta upon L cube. Now if you see what are this applying unit displacement that we are applying at your coordinate 2 and keeping all other coordinates are fixed or no, that means other coordinates are which one? That is your for theta B and theta C, means we are restricting AB and CD member just for the values of translational rotations, but we are keeping those free for your delta values over there. So this translational displacement rotation 12 EI delta upon L cube, that will be emerging at your joint B also and at your joint C also. Okay, that means this 12 EI delta upon L cube, that will be for your member BA also, and plus 12 EI delta upon L cube, that will be for member CD also here. Okay, whereas delta will be again equal to 1, L cube for BA and L cube for CD, that is 4 cube plus 2 cube. If you solve this I am getting as 12 divided by 4 cube plus 12 divided by 2 cube, I've got this as plus 1.687 EI. 1.687 of EI. Okay, if you find any query, you can comment me over there. I'll try to solve over there. Okay, but I hope in your next Roman condition you'll get this very clear. Okay, so next we'll be seeing for Roman number 3. That will be what? We'll apply unit displacement at coordinate 3, keeping all other coordinates fixed. So what you have to do is you have to apply theta c or d3 is equal to 1 now. Okay, and you have to fix the joint B completely for rotation also and for the translational swing displacement also. Okay, so I'll draw the diagram for that. Joint A is already fixed, joint D is also fixed here. Okay, here you are having joint B and joint C. B is also fixed here. Okay, now I'll mark the stiffness coefficient. So at the first coordinate, second coordinate, and at the third coordinate. So this will be S of stiffness at your first coordinate when unit displacement is applied at your third. Stiffness you are calculating at your second coordinate when unit displacement is applied at your third coordinate. Stiffness at your third coordinate you are calculating when unit displacement is also applied at your third coordinate. So I'll get that as S of 3, 3. Right. So for S of 3, 3, S of 1, 3 and S of 2, 3. Now we are applying theta C is equal to 1 there. So we'll see the displacement pattern of CD member. So C will be combination for CB and CD. So this will be a clockwise rotation. So for CB member that will follow upward path over there, which will show this D3 is equal to 1 there. Okay, and same way for this CD member that will be again a clockwise path, which will be on the inner side because moment will originate it from inner side, which will show again here this D3 is equal to 1. Okay, now we'll calculate the values of this. So S of 1, 3, S of 2, 3 and S of 3, 3. One by one we'll see. We'll calculate S of 3, 3 first. Okay, because that is simple. So for corresponding to S of 3, 3, C joint will be the near end joint over there. Okay, so for near end joint that will be for CB and CD member, that will be moment 4 EI theta C upon L for CB plus 4 EI theta C upon L, that is for CD. So if you calculate this 4 by 4 plus 4 by 2, I am getting this as S of 3, 3 is equal to 3 times of EI. Okay, same way I'll calculate S of 1, 3 corresponding to joint C. B will be treated as your farther end over there. So farther end moment will be at your S of 1, 3. So S of 1, 3 I'll get as 2 EI theta C upon L, but that will be only for member BC. For BA it will be completely restrained. So 2 by L or 2 by 4, that I'll get as 0.5 times of EI. Now we'll check whether you are getting equal to S of 3, 1 or not. Okay, S of 1, 3 I am getting 0.5. S of 3, 1 in my first Roman I have got 0.5. Okay, yes, that is same. Now I'll calculate S of 3, 2. Okay, S of 3, 2 is what? That is again the horizontal force. So here which note you will use? Again note number 3. That is if you are applying note number 1. Sorry, if you are applying theta is equal to 1 and if you are calculating force as your stiffness coefficient, so for that force this value comes equal to 6 EI theta C upon L square, and that will be for member CD. That will be for member CD, because why? B joint will not be getting deflected. Whatever this S of 2, 3 is coming, same influence on B and C will be there. So whatever influence of S of 2, 3 is on B, same is on C. So that is why I have considered this for CD. 6 EI theta C upon L square, that is upon L square. Okay, so 6 by L square, if I calculate this I get as minus, L is your 2 here. Okay, so this I am getting as minus 1.5 times of EI. We'll check whether S of 3, 2 you are getting same or not. S of 3, 2 we are getting in Roman 2. See, S of 3, 2 I have got that as minus 1.5 EI. So your all values are getting matched over here. Okay. Now next, we'll write all these values in your matrix form. So F of 1, 2, 3, this I have got as first, 0, right? Second value that I have got as 100 and 0 again. So 0, 100 and 0 is equal to AD L1, L2 and L3, that I am getting as minus 80, 0 and plus 80. Minus 80, 0 and plus 80, plus from S matrix I take I common, EI common. Okay, next S of 1 1, that I have got 2EI. Okay, S of 2 1 I have got as 0.375 and S of 3 1 I am getting as 0.5 over there. Okay, so I'll write all these values first. First I'll write S of 1 1, 2, S of 2 2, that I have got as 1.687, and S of 3 3 I am getting as 3 over here. Next here values I will write. This is your S of 1 2 value, that I have got S of 1 2 as minus 0.375. Same is your value for S of 2 1, that is here minus 0.375. Okay, next S of 1 3 I am getting as 0.5. Same is your value with 0.5, that is S of 3 1, and S of 2 3 I am getting as minus 1.5 and S of 3 2 as minus 1.5 multiplied by D1, D2 and D3. Okay, so if equations I will get from this, so first equation I will get first row multiplied by column, that is 2D1 minus 0.375 of D2 plus 0.5 times of D3 is equal to this 80. After going on RHS it will become positive, so 80 divided by EI, right? That will be our equation number 1. Next, second equation, second row multiplied by column again, minus 0.375 of D1 plus 1.687 of D2 minus 1.5 of D3 is equal to this 0, and here you are having 100, so that will become directly 100 upon EI. Already it is on RHS side, LHS side, so no need of changing its sign. And third one, third row multiplied by column again, so 0.5 times of D1 minus 1.5 times of D2 plus 3 times of D3 is equal to this ongoing, it will become negative 88 upon EI as my equation number 3. Okay, so these three equations I am getting here. Okay, on solving these three equations I am getting D1, that is nothing but your value of theta b, D2, that is nothing but value of your delta b, and D3, that is nothing but your value of theta c, as 53.33 divided by EI. Second value I am getting as 71.15 divided by EI, and third, that is 0.018 divided by EI, are these three values over there. Now using these three values I'll calculate the final moments. So next step will be your slope deflection equations, that is for your first member AB. Okay, is equal to MF AB, that is your 0 plus 2EI upon L, so 2 divided by 4, that becomes 0.5 of EI, into bracket theta A is 0, just what will remain, theta B minus 3 delta upon L. This will be your one basic change in your sway frames over there. You have to consider the delta in your slope deflection equations over there. Okay, now if you calculate this, substitute this delta as it is with your sign in this. Okay, no need of changing here sign, plus or minus, because if your frame is swaying towards right, this will come always minus 3 delta upon L. If it frame sways towards the left, this will come plus over there. So if you calculate this MAB I am getting as minus 0.015 kilonewton meter, or almost 0 you can say. It is a capable support over there, that is a fixed support, yet you are getting bending moment 0. It is okay, but if you are having incapable support and you are not getting that bending moment 0, then that will be a problematic. Okay, next MBA. For MBA MFBA again 0 plus 0.5 EI. This I'll get as 2 theta B minus 3 delta upon L. So again if you substitute this L and theta B and delta values, this I am getting as plus 26.64 over there kilonewton meter. Right. Next MBC. So MBC I am having MFBC for that I have calculated as minus 80 plus 2 EI upon L, again 2 by length is 4, so that will get as 0.5 EI into bracket 2 theta B plus theta C minus 3 delta upon L. So here you have to substitute theta B, delta and theta C also. So substituting this I am getting this as minus 26.64 kilonewton meter. Okay, but here the thing is what, for the sway frames your this delta value that will be always equal to 0. That will be always equal to 0. So if you do not substitute this 71.15 in this equation over there, if you substitute, these values will not get matched over there for your conditions of equilibrium. Here for I have told you the assumptions in sway frame, that is the sway frames will be only harming your column members over there. If your frame is swaying, if your beam is swaying towards the upward or downward direction in vertical direction, then your vertical reactions will remain 0. Okay, but in cases of frames your delta will be 0 for your horizontal member, that is the beam members BC and CP mostly. So here your delta will be 0, so I am getting this as minus 26.64. Next is your MCB, that I am getting MFCB plus 80 plus 0.5 EI theta B plus 2 times of theta C. Here I will not write delta over there. Why? Because that I have to consider here 0. Okay, so this I have got as 106.68. Okay, next is your MCD, that is your MFCD again 0 plus 2 EI upon L. L for CD is your 2 meter. So 2 by 2 that will become 1 EI in bracket 2 times of theta C minus again 3 delta upon L. Theta D will be here 0. Why? Because your D is your fixed support. So for fixed support your theta D will be 0. So this I am getting as minus 106.67 kilonewton meter. And the last moment MDC, that I am getting as MFDC again 0 plus EI theta C minus 3 delta upon L, that I am getting as minus 106.70 kilonewton meter. Okay, so these are the all final moments which I am getting here. Now I will draw the diagram of BMD from this. Joint A, B, C and D here. Okay, at A I am having this moment as minus almost to 0, but I will show some short value over here, that is 0.015. okay, at B I am getting as 26.64 positive, so plus that will be on the outward side. So join these two by a straight line, 26.64 over there. Next for MBC, this I am getting as minus 26.64, that will be on the upward side. Next MCB I am getting plus 106.68, plus it is, so it will be plotted on the upward side again as per your sign conventions. Okay, next MCD, that is your negative, so it will be plotted on the outward side again 106.67, and the last you are getting this again negative, so it will be plotted on the inner side 106.70. Okay, now we will calculate span moment over there. Span moment, only one span we are having loading, that is BC, that is your UDL, so it will come WL square by 8. So W if you substitute, that is 60 into 4 square divided by 8, I am getting this as 120, and that will follow a parabolic path. So this is your WL square by 8 is equal to 120, and just what you have to do is you have to shade this superimposed part here. This gives me BMD by superposition. Okay, so this was the numerical on the sway frames, in that how your frame varies and how you have to use those 3 notes which I have given you. Okay, very effectively. This numerical is also easy, just you have to uh, see the concepts whatever we are going to follow very properly. Okay, and the last thing is you have to consider the delta in your slope deflection equation, because most probably what happens is delta you do not consider while calculating the slope deflection equations, and this values goes wrong over there. Your whole numerical comes correct, but this values goes wrong, and your bending moment also goes wrong over there. So you have to take care of these things. If you are having any query, again you can comment me. Thank you so much.